Question 27 MCQ, Newton's laws of motion, Pathfinder. A homogeneous bar of mass m is released from rest on a fixed inclined plane of inclination theta above the horizontal as shown. The upper part of the plane shown in dark gray is not frictionless and the lower part shown in light gray is frictionless. Coefficient of friction between the bar and the upper part of the plane is mu. What will be the maximum tensile force in the bar while it is sliding on the plane? Acceleration is given due to gravity, that is g. Okay, we have such options. Let's understand this problem carefully because there are actually two important ideas involved here. We have a homogeneous bar of mass m and length L released from rest on an inclined plane. The upper portion of the plane is rough while the lower part is smooth. The upper portion has a coefficient of friction as mu. Now at some instant, suppose a length x of the bar has entered the smooth region like this. So in this figure, this red one is showing the rough part of the surface while this brown color is showing the smooth part of the surface, and this is the position of rod or bar at some instant. And suppose the length of this bar on this smooth surface is x, and let these masses be m dash on the smooth part and m double dash on the rough part. Now if we find acceleration at this instant, it will come out equal to this m dash plus m double dash, that is the total mass of the bar. This is mg sine theta, the component of weight down the plane, and this is the friction force acting on the rough part of the bar and divided by total mass. And writing these masses in terms of their lengths, we can write total mass as lambda into L. Lambda means mass per unit length, and similarly all masses can be written in terms of their lengths. The length of this part of rod lying on the upper surface is L minus x, so you can verify these terms. Now comes the important part. We want to find the maximum tensile force inside this bar. We cannot simply assume that the maximum tension is at the junction at this point. We have to first prove it. So consider a section inside the smooth portion at a distance y from the lower end, and since it is in smooth portion, this y is less than x. For this small portion there is no friction because it is completely on the smooth surface, this part. If we draw FBD, so this part will have a component of its weight down the plane, that is lambda into y, that is mass of this part, into g sine theta. It will have a tensile force here, call it F suppose, and writing Newton's law for this, we'll have this expression. This is simple, F minus this lambda yg sine theta, so this term I have taken on the other side, is equal to ma. So lambda into y is its mass, and this is the acceleration. Acceleration of this part is same as the acceleration of full rod. Okay, so from here on solving we get the value of F. Now for a given x, we are finding that value of y which gives the maximum tension. So what we are seeing that in the smooth portion the tension keeps increasing with y. And what is the largest possible y in the smooth region? It is simply equal to x exactly at the junction. So within the smooth portion the tension is maximum at the junction. But we still have to check the rough region, this region. Now take a section in the rough region at a distance y from the junction. So see the second figure. Now I am considering a section which is y from the junction. So at this section. So now we'll consider this x plus y length of rod and write its equation. So lambda into x plus y, this is the mass of this part, x plus y part. G sine theta, this is the component of weight along the inclined surface. Minus F because F is acting upwards. Minus friction, and friction will not act on this total part. It will act only this y part because that is on rough surface. And this is equal to ma. Okay. And just put the value of A we have found earlier and solve for F, we get this value. Now again think for what value of y this force is going to be a maximum, And since y appears at this position, it's simple that if y becomes minimum, then f will become maximum, and minimum y is 0. So this too is telling that in this rough part, as we increase y, tension is decreasing, so maximum tension is at junction. So now we have arrived to this conclusion that the tension is maximum at the junction. Now we have to find the tension at the junction. For that, put either y equal to x in this expression or y equal to 0 in this expression. These two will get the same result. So we have found this value of f at the junction. Now let x vary. Up till now we have found the tension is maximum at the junction for any given value of x. Now we have to find absolute maximum tension. For that we have to vary x as well and see where this f goes to a maximum value. So for that we'll put d by dx of this force equal to 0 and find the value of x as L by 2. Put this value of x back into the expression of f to find this expression. Put lambda into L as mass. So we are getting this result, which is option B. Okay. So it's a nice question because in it we have to find two things. First, for a given x, where is the tension maximum? And second, for what value of x that tension is maximum. Okay.